Welcome back to Whispering Universes, where we journey to the quietest corners of the cosmos and explore the frozen mysteries that drift in the darkness beyond the planets. Tonight, we travel to a realm so distant that the Sun appears as little more than a brilliant star, a place where temperatures hover just above absolute zero, where billions of icy bodies orbit in the perpetual twilight at the edge of our solar system. We're heading to the Kuiper Belt, a vast disk of frozen wanderers that holds secrets from the very dawn of planetary formation, where time moves slowly and change comes measured in millions of years. Imagine standing on one of these distant worlds, if such a thing were possible. The Sun, that blazing sphere that dominates our daylight sky here on Earth, would appear 1,000 times dimmer, casting a pale glow across landscapes of nitrogen ice and frozen methane. You would see no blue sky, for there is barely any atmosphere to scatter light. Instead, you would gaze upon a field of stars so brilliant, so numerous, that the Milky Way would seem close enough to touch. Around you, ancient ice would lie undisturbed, perhaps for billions of years, a surface that remembers the conditions present when our solar system was young, when the planets were still forming, and Earth itself was a molten sphere, cooling in the inner darkness. The Kuiper Belt stretches from roughly 30 astronomical units from the Sun, just beyond Neptune's orbit, to perhaps 55 astronomical units outward, encompassing a volume so vast that it staggers the imagination. 1 astronomical unit equals the distance from Earth to the Sun, about 150 million kilometers. And so, we're speaking of a region that begins 4.5 billion kilometers from our star and extends billions more kilometers beyond that. Within this immense volume drift hundreds of thousands of objects we've detected, and likely millions or billions more too small or distant for our telescopes to yet resolve. They range from mountain-sized chunks of ice and rock to worlds hundreds or even thousands of kilometers across, each one following its own elliptical path around the Sun, each one a time capsule from an era long before the first single-celled organisms appeared in Earth's ancient oceans. For most of human history, we didn't know this realm existed. Ancient astronomers tracked the planets visible to the naked eye, those wandering lights that moved against the fixed stars. Even after telescopes revealed Uranus and Neptune, the idea that our solar system extended much farther into a populated zone of countless frozen bodies remained unknown. The planets seemed to end at Neptune, with perhaps some comets occasionally visiting from unknown distances. But in the middle of the 20th century, astronomers began to suspect that something else must lie beyond, that the comets we saw weren't coming from infinitely far away, but from a more structured reservoir much closer to home. The theoretical predictions came first, the patient reasoning that led scientists to conclude something had to be there even before they could see it. Tonight we'll trace the story of how we discovered this distant realm, how our understanding has transformed from vague hypothesis to detailed census, how missions like New Horizons have revealed these frozen worlds in stunning clarity. We'll explore the physics of these extreme environments, where temperatures rarely rise above 40 Kelvin, where water ice becomes as hard as granite and methane falls as snow. We'll meet the population of dwarf planets, including Pluto and its family, and understand why these objects have revolutionized our conception of what a solar system looks like. We'll consider the architecture of the Kuiper Belt, shaped by gravitational resonances with Neptune, by ancient migration of the giant planets, by collisions and capture over billions of years. And we'll contemplate what these icy wanderers mean for our understanding of cosmic origins. The Kuiper Belt preserves materials and conditions from the solar nebula, that rotating disk of gas and dust from which all the planets formed 4.6 billion years ago. By studying these objects, we're reading a record written in ice and stone, a chronicle of planetary birth and evolution that connects us to the deepest history of our cosmic home. These aren't just distant rocks and ice balls, they're messengers from the dawn of the solar system, carrying information about chemistry and physics and the processes that created everything we see around us, including the very atoms that make up our bodies and the world we inhabit. As you settle into comfort, as your breathing slows and your thoughts begin to drift like those distant frozen worlds, let yourself travel with us to the edge, to the boundary where our solar system fades into the interstellar medium, where the solar wind becomes indistinguishable from the background pressure of the galaxy itself. Here on Whispering Universes, we find peace in understanding these remote places, in following the patient work of scientists who dedicate their lives to mapping and comprehending realms so far away that light takes hours to reach them. The Kuiper Belt awaits, silent and ancient, and tonight we'll explore its frozen mysteries together, gently, contemplatively, as sleep approaches and the boundaries between distant cosmic realms and the landscape of dreams begin to soften and merge. The story of the Kuiper Belt begins not with a telescope observation, but with a problem, a mystery in the orbits of comets that pointed towards something hidden beyond Neptune. In 1943, an Irish astronomer named Kenneth Edgeworth published a paper suggesting that the solar nebula, that disk of material from which the planets formed, probably didn't just abruptly stop at Neptune's orbit. He reasoned that in the outer regions of this disk, where material was more sparse and collisions less frequent, planetesimals, those building blocks of worlds, might never have fully accreted into planets. Instead, they would remain as a population of smaller bodies, gradually cleared by gravitational interactions, but never entirely depleted. His reasoning was sound, grounded in what was known about planetary formation, but the paper attracted little attention at the time, and Edgeworth's insight would remain largely forgotten for decades. 8 years later, in 1951, a Dutch-American astronomer named Gerard Kuiper independently arrived at a similar conclusion, though through slightly different reasoning. Kuiper, working at the University of Chicago's Yerkes Observatory, published a paper examining the origins of the solar system and the distribution of comets. He noted that short-period comets, those with orbital periods less than 200 years, had a peculiar characteristic. Unlike long-period comets that arrived from all directions, suggesting a spherical distribution around the Sun, short-period comets had orbits that stayed close to the plane of the planets, the ecliptic. This suggested they originated from a disk-like structure rather than a sphere. Kuiper proposed that beyond Neptune, there must exist a belt of icy bodies, remnants from planetary formation, and that gravitational interactions occasionally sent these objects sunward, where they became the short-period comets we observed. The mathematics of orbital mechanics supported this hypothesis. Comets lose mass each time they pass close to the Sun, their ices sublimating away, creating those spectacular tails we see from Earth. A typical comet might survive a few hundred passes through the inner solar system before completely evaporating or fragmenting. Yet we continued to see short-period comets, which meant they must be continuously resupplied from somewhere. If all comets came from the theorized Oort cloud, that spherical shell of comets at the very edge of the solar system's gravitational influence, their orbits should be randomly distributed. The fact that short-period comets orbited in the same plane as the planets pointed to a closer, disk-like source. Through the 1960s and 1970s, as our understanding of planetary formation evolved, the theoretical arguments for Kuiper's belt became stronger. Computer models of the early solar system showed that Neptune likely formed closer to the Sun and migrated outward over millions of years, its gravitational influence clearing some material but scattering much more into distant orbits. This migration would have created a complex structure of orbital resonances, regions where objects completed orbits in simple integer ratios with Neptune's orbital period. Objects caught in these resonances would be protected from close encounters with Neptune, allowing them to survive over billions of years. The theory predicted not just a belt of objects, but a structured population, organized by the subtle gravitational influence of the outermost giant planet. Still, theory is one thing and observation another. Throughout the 1970s and 1980s, no confirmed Kuiper Belt objects had been detected. The problem was one of brightness and distance. Even a world hundreds of kilometers across, at a distance of 40 or 50 astronomical units from the Sun, would appear incredibly faint. The inverse square law means that an object at 40 astronomical units receives 1,600 times less sunlight than Earth does, and reflects proportionally less light back toward us. Early charge-coupled device, or CCD detectors, were helping revolutionize astronomy, but the sensitivity and field of view needed to survey large areas of sky for faint, slow-moving objects remained challenging. Astronomers knew roughly where to look, along the ecliptic in the region beyond Neptune, but finding needle-like points of light among millions of background stars required patience, technology, and dedicated telescope time. By the late 1980s, several teams of astronomers had begun systematic searches. They would take images of the same region of sky separated by hours or days, then carefully compare them to identify anything that had moved. Stars would remain fixed, but a Kuiper Belt object orbiting the Sun would shift position slightly between images. The work was painstaking, involving thousands of images and countless hours of analysis. But the theoretical arguments had become compelling enough that researchers believed success was only a matter of time and effort. Somewhere out there, beyond Neptune in the cold darkness, a population of frozen worlds waited to be discovered, objects that would transform our understanding of the solar system's architecture and history. The prediction had been made decades earlier. Now, as the 1990s approached, the technology and dedication finally aligned to test whether Gerard Kuiper and Kenneth Edgeworth had been right. On the night of August 30th, 1992, using the 2.2-meter telescope at the Mauna Kea Observatory in Hawaii, astronomers David Dewitt and Jane Liu made a discovery that would reshape the map of the solar system. After nearly 5 years of systematic searching, after examining thousands of images and tracking hundreds of false positives, they detected a faint object moving slowly against the background stars in the constellation Pisces. They designated it 1992 Cubion, following the naming conventions for newly discovered solar system objects, and subsequent observations confirmed what they suspected. This was not an asteroid from the main belt, not a comet with a coma or tail, but something else entirely. Something orbiting beyond Neptune in the region Gerard Kuiper had predicted 4 decades earlier. The Kuiper Belt, previously only theoretical, had revealed its first confirmed member. The discovery came after years of preparation and previous disappointments. Dewitt, originally from London and working at the University of Hawaii, had become intrigued by the problem of where short-period comets originated. In 1987, he recruited Liu, who had recently completed her doctorate, to join him in a systematic search of the sky beyond Neptune. They estimated they would need to survey a substantial area and reach objects down to magnitude 25 or fainter, about 100 million times dimmer than stars visible to the naked eye. This required not only sensitive detectors, but also clear dark skies and considerable telescope time, resources that had to be carefully requested and justified to the committees that allocated time on major observatories. Their search strategy involved taking multiple images of the same field, separated by several hours, then carefully blinking between them, looking for objects that had shifted position. A Kuiper Belt object at 40 astronomical units, moving in its orbit around the Sun, would appear to drift very slowly against the background stars, perhaps 2 or 3 arc-seconds per hour. An arc-second is 1/3600th of a degree, an extraordinarily small angle. To put this in perspective, the full moon spans about 1,800 arc-seconds, so a Kuiper Belt object might move the width of the moon across the sky over the course of a month. Detecting this required images sharp enough to resolve such tiny shifts, and the patience to methodically examine field after field, night after night, for years. When 1992 QB1 finally appeared, moving exactly as predicted for an object orbiting at roughly 44 astronomical units, the confirmation brought both excitement and vindication. Follow-up observations over subsequent months allowed astronomers to calculate its orbit with precision. It moved in a nearly circular path beyond Neptune, tilted only slightly relative to the plane of the planets, exactly where theory predicted Kuiper Belt objects should exist. Its brightness suggested it was perhaps 200 to 300 kilometers across, a substantial world of ice and rock that had been orbiting unseen for billions of years. And most importantly, the discovery implied it wasn't alone. If one object existed in this region, probability suggested many more awaited detection. They didn't have to wait long. In March 1993, Jewett and Liu discovered a second Kuiper Belt object, designated 1993 FBO. Over the following months and years, as they continued their survey, and as other teams joined the search, the trickle became a stream. By the end of 1993, more than a dozen Kuiper Belt objects had been confirmed. By 2000, the count exceeded 300. By 2010, more than 1,000. Today, we've catalogued over 3,000 objects in the Kuiper Belt and scattered disk, and the true population certainly numbers in the hundreds of thousands for objects larger than 100 kilometers, with millions more smaller bodies. The discovery of 1992 QB1 represented one of those pivotal moments in astronomy, when a theoretical prediction, made through careful reasoning about physics and orbits, receives direct observational confirmation. Kenneth Edgeworth had suggested it in 1943, Gerard Kuiper had developed the idea in 1951, and now, more than 40 years after Kuiper's paper, technological advancement, and dedicated searching had finally revealed the reality of this distant realm. The solar system, it turned out, didn't end with Neptune. Beyond the last gas giant lay a vast zone of smaller bodies, a disk of icy worlds that represented the remnants of planetary formation, a population that would require years of further study to properly characterize and understand. The discovery also demonstrated the power of systematic surveying and the importance of persistence in astronomy. Jewett and Liu could have given up after 2 years, after 3 years, after facing skepticism about whether the search was worth the telescope time. But they continued, refining their techniques, improving their detection methods, believing that the theoretical arguments were sound and that success required only patience and care. When 1992 QB1 finally appeared on their images, it validated not just 5 years of searching, but decades of theoretical work by planetary scientists who had reasoned their way toward understanding this distant frontier before anyone had actually seen it. The first glimpse of the Kuiper Belt opened a new chapter in solar system exploration, one we're still writing today as missions venture into this frozen realm and telescopes continue to catalogue its population. Following the confirmation of 1992 QB1, the pace of Kuiper Belt discoveries accelerated dramatically as multiple teams around the world joined the search. Improved CCD detectors, more sophisticated image processing software, and dedicated survey programs transformed what had been a difficult pioneering effort into something approaching a systematic census. By the late 1990s, astronomers were discovering several new Kuiper Belt objects per month. By the 2000s, automated sky surveys were detecting dozens per year, and with each new discovery, the complexity and structure of this distant population became more apparent. The Kuiper Belt wasn't a uniform disk of objects, but rather a diverse collection of distinct populations, each with its own orbital characteristics and historical story. Astronomers began classifying Kuiper Belt objects based on their orbital properties. The classical Kuiper Belt, sometimes called the cold classical belt, consists of objects on nearly circular orbits with low inclinations relative to the plane of the planets. These objects, like 1992 QB1, orbit between roughly 42 and 47 astronomical units from the Sun, and appear to have been minimally disturbed since the solar system formed. They're called cold, not because their physical temperature differs significantly from other Kuiper Belt objects, but because their orbital velocities are relatively low, following the astronomical convention that equates higher orbital velocities with hotter dynamical populations. These objects represent the most pristine remnants of the original protoplanetary disk, time capsules that have experienced relatively little gravitational scattering or collisional evolution. A second population, the resonant Kuiper Belt, consists of objects locked in orbital resonances with Neptune. The most prominent of these is the 3-2 resonance, where objects complete 3 orbits around the Sun for every 2 orbits Neptune completes. Objects in this resonance orbit at approximately 39.5 astronomical units, and the most famous member of this population is Pluto itself, along with hundreds of other objects astronomers call Plutinos. Other resonances exist as well. The 2-1 resonance at about 48 astronomical units, the 5.2 resonance, the 7.4 resonance, each one representing a gravitational relationship with Neptune that protects objects from close encounters and allows them to survive over billions of years. These resonances were likely populated during Neptune's outward migration in the early solar system, when the giant planet swept up some objects and captured others into stable resonant orbits. Beyond the classical belt lies the scattered disk, a population on highly elliptical and often steeply inclined orbits that can take objects from 30 astronomical units at closest approach to several hundred astronomical units at their most distant. These objects show clear signs of having been strongly scattered by gravitational interactions. With Neptune flung into extreme orbits that occasionally bring them back to the inner edge of the Kuiper Belt, the scattered disk merges gradually with the detached population, objects on orbits so distant at their closest approach that they no longer interact significantly with Neptune. These detached objects, which we'll explore more in later chapters, represent perhaps the most mysterious population, as their current orbits require explanation through past encounters or the possible gravitational influence of yet undiscovered massive bodies in the outer solar system. The size distribution of Kuiper Belt objects also revealed important clues about their history. Astronomers found that the population includes everything from small bodies just a few kilometers across up to dwarf planets over 2,000 kilometers in diameter. The distribution isn't random, but follows a power law, meaning there are many more small objects than large ones, roughly what you'd expect from a population that formed through accretion and has been subsequently modified by collisions. However, there appears to be a deficit of very small objects compared to what simple collision models would predict, suggesting that the Kuiper Belt has lost much of its original population over the age of the solar system, either through collisions that ground bodies down to dust or through gravitational ejection into interstellar space. By the 2010s, advanced surveys like the Pan-STARRS project in Hawaii were pushing the detection limits even further, finding objects down to magnitude 26 or fainter. These surveys revealed that the Kuiper Belt extends further than initially thought, with objects detected beyond 55 astronomical units, and that the populations show subtle structure in their orbital distributions, hints of past gravitational perturbations and dynamical evolution. Each new discovery added to our statistical understanding, helping astronomers reconstruct the history of the outer solar system, test models of planet migration and formation, and predict what future observations might reveal. Today, we've catalogued over 3,000 Kuiper Belt and scattered disk objects, and spectroscopic observations have begun revealing their compositions, their colours, their surface properties. This census remains incomplete. Current estimates suggest there may be 70,000 objects larger than 100 kilometers in diameter, and perhaps tens of millions of comet-sized bodies most still too faint and distant for our telescopes to detect. But the population that has emerged from darkness over the past 3 decades has already revolutionized our understanding. What began as a prediction about where short-period comets might originate has become a detailed picture of a vast reservoir of primitive material, a region that holds clues to how planetary systems form, how they evolve, and what they leave behind in their outer reaches. The Kuiper Belt is no longer theoretical, no longer a vague hypothesis, but a mapped and studied frontier, and yet it continues to surprise us with each new observation, each new world that emerges from the twilight at the edge of our solar system. Perhaps no single object has been more transformed by the discovery of the Kuiper Belt than Pluto itself. Discovered in 1930 by Clyde Tombaugh during a systematic search for a hypothetical Planet X, Pluto reigned for 76 years as the 9th planet, the smallest and most distant world in the solar system. Children memorized it in school. Mnemonics included it. Planetary diagrams showed it as the final outpost before interstellar space. But as the Kuiper Belt population emerged from darkness through the 1990s and early 2000s, Pluto's true nature became increasingly apparent. It wasn't a lone oddball, but rather the first discovered and largest prominent member of a vast population of similar objects. Pluto, it turned out, had a family, and understanding this family would require rethinking what we meant when we called something a planet. The realization came gradually. In the late 1990s, astronomers discovered several Kuiper Belt objects approaching Pluto's size. In 2002, they discovered Quaoar, about half Pluto's diameter. In 2004, they found Orcus, Haumea, and other large objects. Then in 2005, came the discovery that forced a reckoning. A team led by Mike Brown at Caltech announced they had found an object designated 2003 UB313, later named Eris, which appeared to be at least as large as Pluto and possibly larger. Orbiting at an average distance of 68 astronomical units from the Sun, on a highly eccentric and steeply inclined orbit, Eris was undeniably a Kuiper Belt object. But if Eris deserved planet status based on size, and if searchers were likely to discover even more such objects, the number of planets in our solar system could grow unpredictably. The International Astronomical Union faced a choice. They could continue adding planets as large Kuiper Belt objects were discovered, potentially inflating the planet count to dozens or more. Or they could establish a clear definition of what constitutes a planet and reclassify some objects accordingly. In August 2006, at their Triennial General Assembly in Prague, they chose the latter path. After considerable debate, they established 3 criteria for planetary status. A planet must orbit the Sun, must be massive enough that its own gravity pulls it into a roughly spherical shape, and must have cleared the neighbourhood around its orbit of other bodies. Pluto met the first 2 criteria, but not the third. It shares the outer solar system with thousands of other Kuiper Belt objects, and hasn't gravitationally dominated its region the way the 8 larger planets have. The IAU created a new category called dwarf planets for objects that met the first 2 criteria, but not the third. Pluto became the prototype dwarf planet, joined immediately by Eris, and later by Ceres in the asteroid belt Makemake and Haumea. The decision sparked controversy and discussion that continues today. Many planetary scientists disagreed with the definition, arguing that clearing the neighbourhood was an arbitrary criterion that discriminated against objects in distant orbits, where clearing would take far longer than the age of the solar system. Others pointed out that Earth hasn't completely cleared its orbit either, sharing space with thousands of near-Earth asteroids. The debate reflected deeper questions about whether categorization in astronomy should follow tradition or logic, about whether Pluto's cultural significance as a planet outweighed the scientific understanding of its true nature. But setting aside the classification debate, the recognition that Pluto is fundamentally a Kuiper Belt object, the largest clearly identified member of that population, has enriched our understanding of both Pluto and its realm. Pluto orbits in the 3-2 resonance with Neptune, along with hundreds of Plutonos. This resonant protection has allowed it to survive for billions of years, despite crossing Neptune's orbit at its closest approach, which would normally lead to gravitational ejection. Pluto's highly elliptical orbit, tilted 17 degrees relative to the plane of the planets, is typical of resonant Kuiper Belt objects, as is its composition, dominated by nitrogen, methane and water ice. Moreover, Pluto isn't alone. It has 5 known moons, the largest being Charon, which is so massive relative to Pluto that the two orbit a common centre of mass located between them, making them more like a binary system than a planet and satellite. The other moons, Styx, Nix, Kerberos and Hydra, are much smaller and likely formed from debris ejected during the giant impact that created Charon. This satellite system demonstrates that Kuiper Belt objects can be complex worlds with their own gravitational families, their own geological histories, their own stories of formation and evolution that rival those of the classical planets. The reclassification of Pluto, controversial as it was, forced a broader understanding of solar system architecture. Rather than being arbitrary outcasts, the objects we now call dwarf planets represent a transition between the dominant planets that gravitationally sculpted their regions and the smaller bodies that populate the asteroid belt, Kuiper Belt, and beyond. Understanding Pluto as the first discovered member of the Kuiper Belt population, rather than as an anomalous 9th planet, allows us to see patterns and relationships that would otherwise remain hidden. Pluto isn't diminished by being recognized as a dwarf planet and Kuiper Belt object. If anything, it's enriched, placed in context with a vast family of similar worlds that share its frozen realm at the edge of sleep, each one carrying information about the solar system's birth and the processes that created everything we see around us, from Mercury to the scattered disk beyond. To understand the Kuiper Belt requires understanding Neptune's gravitational influence, the subtle ways that the outermost giant planet has shaped and continues to shape the population of objects in the outer solar system. Gravity, that seemingly simple force described by Newton's inverse square law and refined by Einstein's general relativity, creates astonishingly complex dynamics when multiple bodies interact over long timescales. Neptune, with 17 times Earth's mass, orbiting at 30 astronomical units from the Sun, acts as a gravitational shepherd, its influence reaching far beyond its immediate vicinity to organize and sculpt the Kuiper Belt into the structured populations we observe today. The most prominent feature of this gravitational architecture is the system of orbital resonances. A resonance occurs when two orbiting bodies have periods that form a simple integer ratio, creating a repetitive pattern of gravitational tugs that can either destabilize orbits or paradoxically stabilize them over billions of years. The 3.2 resonance, where Pluto and hundreds of Plutonos reside, means these objects orbit the Sun 3 times, while Neptune orbits twice. Every 2 Neptune orbits, the objects return to roughly the same configuration, and while they periodically approach Neptune's orbit, the resonance protects them from close encounters. It's like a cosmic dance, where the partners never actually collide because their choreography is precisely synchronized. Other resonances populate the Kuiper Belt at different distances. The 201 resonance, at approximately 47.8 astronomical units, contains objects called Toutinos. The 5.2 resonance, at about 55 astronomical units, marks what some consider the outer edge of the main Kuiper Belt. The 3.1 resonance, at roughly 62 astronomical units, represents a particularly unstable location where objects are rapidly ejected. Each resonance has its own character, some acting as stable havens where objects can survive indefinitely, others serving as regions of instability that quickly clear themselves of any bodies that wander into them. Mapping these resonances and understanding their populations tells us about the history of the outer solar system, about how objects were captured and scattered over time. The classical Kuiper Belt, orbiting between these resonances with low eccentricity and inclination, occupies a sweet spot where Neptune's influence is present but not overwhelming. These objects likely formed in place, relatively undisturbed by the migrations and scatterings that affected other populations. Their orbits preserve information about the original configuration of the outer solar system before the giant planets reached their current positions. Computer simulations suggest that Jupiter, Saturn, Uranus, and Neptune didn't form where we find them today, but rather closer together, and that gravitational interactions caused them to migrate. Jupiter moving slightly inward, while Saturn, Uranus, and Neptune moved outward over tens of millions of years. This migration, particularly Neptune's outward journey from perhaps 20 astronomical units to its current 30 astronomical units, profoundly affected the Kuiper Belt. As Neptune migrated, it scattered objects outward, some into distant orbits, some into resonances, some ejected entirely from the solar system. The NICE model, named for the French city where it was developed, describes how the giant planet's migration could have triggered the late heavy bombardment, that period about 3.9 billion years ago when the inner solar system experienced intense cratering as scattered objects rained inward. The Kuiper Belt we see today represents the survivors of this ancient upheaval, the objects that weren't ejected or destroyed, organized by resonances and separated into distinct dynamical populations based on how they interacted with Neptune during its migration. Beyond the classical belt lies the scattered disk, objects on highly elliptical orbits that Neptune continues to perturb. These bodies venture far from the Sun at their most distant, sometimes hundreds of astronomical units, but their orbits bring them back close enough to Neptune's region that gravitational interactions remain significant over time. The scattered disk represents ongoing scattering, objects still being actively pushed around by Neptune's gravity. Some will eventually be ejected from the solar system entirely. Others might be captured into resonances or have their orbits circularized through complex multi-body interactions. The scattered disk is the most dynamically active region of the trans-Neptunian population, a zone where orbits change on timescales of millions rather than billions of years. Even farther out, the detached population begins, objects whose closest approach to the Sun lies beyond Neptune's strong gravitational influence. These bodies, which include objects like Sedna, with its extremely distant orbit, pose a mystery. Their current orbits can't be easily explained by interactions with Neptune alone, suggesting they were either placed on these orbits during the solar system's formation through interactions with other massive bodies, or that they've been perturbed by something else, perhaps passing stars when our solar system was young and still embedded in its birth cluster, or possibly by an as-yet undiscovered massive planet in the very distant outer solar system, a topic we'll explore in detail in later chapters. The architecture of the outer solar system extends even beyond the detached population to the heliopause, the boundary where the solar wind, that stream of charged particles flowing from the Sun, is balanced by the pressure of the interstellar medium. The Voyager spacecraft crossed this boundary at about 120 astronomical units, entering the space between stars. The Kuiper Belt occupies the inner portion of this vast realm, the region where the Sun's gravity still dominates, but its light has faded to near starlight intensity, where planetary formation began but never fully completed, leaving behind this population of icy worlds that serves as both cemetery and nursery, both end and beginning, the edge where our solar system finally gives way to the galaxy beyond. To understand why the Kuiper Belt exists requires journeying back 4.6 billion years to the birth of the solar system itself, to that vast rotating cloud of gas and dust that astronomers call the Solar Nebula. This nebula, formed from material ejected by previous generations of stars, contained all the ingredients needed to create planets, moons, and the countless smaller bodies that populate our cosmic neighborhood. The nebula's composition reflected billions of years of stellar nucleosynthesis, mostly hydrogen and helium from the Big Bang, but enriched with heavier elements forged in stellar cores and supernova explosions. From this chemical inventory, gravity and physics would construct everything we see today, including the frozen worlds of the Kuiper Belt. The formation process began with gravitational collapse. Some disturbance, perhaps a shockwave from a nearby supernova, or the compression from a passing density wave in our galaxy, caused the nebula to begin contracting. As it collapsed, conservation of angular momentum caused it to spin faster, and centrifugal force flattened it into a disk, with most of the mass falling toward the center, where pressure and temperature rose until hydrogen fusion ignited, creating the Sun. But the disk retained perhaps 1% of the total mass, and within this disk, the process of planetary formation unfolded over millions of years through a complex sequence of growth stages that proceeded differently at different distances from the new star. Close to the Sun, where temperatures exceeded several hundred Kelvin, only materials with high vaporization temperatures could condense into solid form. Metals and silicate minerals formed tiny grains that collided and stuck together, beginning the growth toward planets. But volatile materials, water, methane, ammonia, remained gaseous and couldn't contribute to solid growth. This is why the inner planets, Mercury, Venus, Earth, and Mars, are relatively small and rocky. Beyond about 3 astronomical units, where temperatures dropped below water's freezing point, the frost line marked a crucial transition. Here, water ice could condense, roughly doubling the amount of solid material available for planet building. This allowed the formation of much larger cores, which once they reached about 10 Earth masses, had sufficient gravity to begin capturing hydrogen and helium directly from the nebula, growing into gas giants. In the outer solar system, beyond where Uranus and Neptune formed, temperatures were even lower, allowing methane, ammonia, and other volatiles to freeze. Here, the solar nebula was also less dense, with material spread over greater distances and orbital velocities lower. These conditions affected how planetary formation proceeded. Planetesimals, those kilometer-sized building blocks, formed through the gradual accumulation of smaller particles. When two planetesimals collided, they might stick together if the collision was gentle enough, or shatter into fragments if the impact was too violent. The balance between growth through accretion and destruction through collision determined whether bodies could grow into planets or remained as smaller objects. In the region we now call the Kuiper Belt, several factors prevented the formation of a single large planet. First, the surface density of material was relatively low, meaning that the building blocks were spread thin and collisions happened less frequently. Second, orbital velocities decreased with distance from the Sun, following Kepler's laws, so objects moved more slowly relative to one another. While this might seem like it would help accretion by making collisions gentler, it also meant that objects took longer to encounter each other and that gravitational focusing, the effect where gravity bends the trajectories of approaching bodies to make collisions more likely, became less effective. Third, and perhaps most importantly, Neptune's outward migration disrupted the formation process before it could complete. Computer simulations of the early solar system suggest that Neptune formed closer to the Sun, perhaps around 15 or 20 astronomical units, where material density was higher and formation timescales were shorter. As Neptune grew to its final mass and interacted gravitationally with the remaining disk material and with the other giant planets, it migrated outward, scattering planetesimals ahead of it and capturing some into resonances. This migration happened relatively early, within the first 100 million years of the solar system's history, but it came late enough that substantial bodies had already formed in what would become the Kuiper Belt region. Some of these bodies were scattered outward into distant orbits or ejected from the solar system entirely. Others were captured into resonances or had their orbits excited to higher eccentricities and inclinations. The relatively gentle orbits that would have facilitated further growth were disrupted, freezing the accretion process before large planets could form. The objects that survived this period of disruption became the Kuiper Belt we observe today. They represent an intermediate stage of planet formation, bodies that had grown beyond the initial kilometer-sized planetesimal stage, but never completed the journey to planetary status. The largest, like Pluto, Eris, Makemake, and Haumea, reached diameters of 1,000 to 2,500 kilometers, large enough that their gravity pulled them into roughly spherical shapes and allowed some geological differentiation between ice-rich mantles and rock-rich cores. But they never grew massive enough to clear their orbital zones or to capture significant atmospheres from the nebula before the sun's radiation and stellar wind dispersed the remaining gas. The composition of Kuiper Belt objects reflects the conditions in the outer solar nebula where they formed. Spectroscopic observations reveal surfaces rich in water ice, methane ice, ammonia ice, and complex organic compounds called tholins, reddish materials formed when simple molecules are irradiated by ultraviolet light and cosmic rays. Some objects show evidence of carbon dioxide ice, nitrogen ice, and even ethane. These are the ices that condense at temperatures between 40 and 70 Kelvin, the temperature range that existed in the outer solar nebula beyond about 30 astronomical units. Mixed with the ice are silicate minerals and perhaps some metals, the refractory materials that could condense at any distance from the Sun, giving Kuiper Belt objects their rock ice composition with typical densities around 1 to 2 grams per cubic centimeter, substantially less than Earth's 5.5 grams per cubic centimeter, but denser than pure water ice. What makes the Kuiper Belt particularly valuable for understanding solar system formation is that these objects have remained largely unchanged since they formed. Unlike Earth, where plate tectonics, erosion and life have thoroughly processed and recycled surface materials, or like the gas giants, where we can't directly observe their formation materials beneath thick atmospheres, Kuiper Belt objects are essentially time capsules. Their surfaces, shielded from the sun's heat by vast distance, preserve the original ices and organic compounds from the solar nebula. Occasional impacts have mixed surface and subsurface materials, and cosmic ray bombardment has processed the top few meters, but overall, studying Kuiper Belt objects is like studying samples from 4.6 billion years ago, from the era when planets were being born and Earth was still a molten proto-world accreting from impacts. The formation scenario also explains why we see the particular populations and distributions we observe. The classical Kuiper Belt objects, with their low eccentricity, low inclination orbits, formed in place and experienced minimal gravitational scattering, preserving their original orbital configuration. The resonant populations were captured during Neptune's migration, when objects happened to be in the right place at the right time to be swept into stable resonances rather than scattered away. The scattered disk represents objects that received strong gravitational kicks but weren't ejected entirely, leaving them on highly elliptical orbits that still interact with Neptune. Each population tells part of the story of how the outer solar system evolved from a relatively smooth disk of material into the complex architecture we map today. As we drift deeper into this exploration, as the boundaries between past and present soften in the hypnagogic space between waking and sleep, consider that every object in the Kuiper Belt carries within its frozen structure a record of the solar system's birth. The precise ratio of different isotopes in the ice, the mixture of crystalline and amorphous water ice, the abundance of organic compounds. All these details encode information about temperature, pressure, chemical processes, and timescales from 4.6 billion years ago. By studying these frozen archives, we're not just learning about distant icy bodies. We're reading the history of how our entire solar system, including the world we inhabit, came into existence from a rotating cloud of stellar debris in the galactic disk, sculpted by gravity and time into the remarkable diversity of worlds we continue to discover and explore. The materials that compose Kuiper Belt objects represent a frozen inventory of the outer solar nebula's chemical composition, substances that condensed into solid form at temperatures barely above absolute zero and have remained largely unaltered for billions of years. Understanding these compositions requires piecing together evidence from multiple sources, spectroscopic observations that reveal what types of ice cover object surfaces, density measurements from objects with moons that allow mass determination, theoretical models of how materials behave at extreme cold, and direct observations from spacecraft like New Horizons that have visited these distant realms and returned detailed compositional maps. What emerges is a picture of worlds built primarily from water ice mixed with more volatile ices like methane, nitrogen, and carbon monoxide, all embedded with darker organic compounds and rocky materials. Water ice dominates most Kuiper Belt object compositions, which makes sense given that oxygen was the third most abundant element in the solar nebula, after hydrogen and helium, and water is the most stable oxygen-hydrogen compound. At the temperatures found in the Kuiper Belt, typically 40 to 50 Kelvin, water ice becomes harder than granite on Earth, with properties more like rock than what we think of when we imagine ice. This water ice can exist in two forms: crystalline, where molecules are arranged in organized hexagonal patterns, and amorphous, where molecules are frozen in disordered configurations. The presence of crystalline water ice on some Kuiper Belt objects poses an interesting puzzle, because forming crystalline ice requires either formation at temperatures above about 100 Kelvin or subsequent heating that allowed amorphous ice to transition to the crystalline form. Finding crystalline water ice on objects that have been frozen at 40 Kelvin for billions of years suggests these bodies have experienced heating events, perhaps from internal radioactive decay early in their history, or from large impacts that locally melted and refroze material. Beyond water ice, spectroscopic observations reveal the presence of more volatile materials, substances that would be gases at Earth's temperature and pressure, but freeze solid in the Kuiper Belt's extreme cold. Methane ice composed of carbon and hydrogen shows up on many objects, particularly the larger ones like Pluto and Eris. Methane has a relatively high vapor pressure even at Kuiper Belt temperatures, meaning it slowly sublimes away over time. The fact that we still see methane ice on objects billions of years old suggests either these objects are cold enough that sublimation is extremely slow, or that fresh methane is being replenished from subsurface reservoirs, possibly through cryovolcanic processes where liquid water or water-ammonia mixtures erupt from the interior and bring dissolved volatiles to the surface. Nitrogen ice, detected prominently on Pluto's surface in New Horizons images, represents an even more volatile substance. At Pluto's temperature of around 40 Kelvin, nitrogen ice is relatively mobile, flowing slowly like glaciers on Earth, filling in basins and creating smooth plains. The same is true for carbon monoxide ice and methane ice, which can mix together and with nitrogen to create a variety of different surface types depending on local conditions. These volatile ices create what planetary scientists call an ice-rich surface that can evolve over time through sublimation and recondensation. driven by slight temperature variations across the surface due to different amounts of sunlight absorption by darker and lighter materials. The reddish colours seen on many Kuiper Belt objects come from organic compounds called tholins, a term coined by astronomer Carl Sagan to describe complex molecules formed when simpler compounds are exposed to ultraviolet radiation or energetic particles. In the Kuiper Belt, cosmic rays and solar ultraviolet light strike methane and other molecules on object surfaces, breaking chemical bonds and allowing atoms to recombine into larger, more complex molecules. Over billions of years, this radiation processing creates a layer of reddish-brown organic material that gives many objects their characteristic coloration. These tholins are similar to materials found on other outer solar system bodies like Saturn's moon Titan and Neptune's moon Triton, suggesting similar chemistry operates wherever methane and other simple organic molecules are exposed to radiation. Beneath the icy surfaces, theoretical models and density measurements suggest Kuiper Belt objects contain substantial amounts of rocky material, silicate minerals, and possibly some metals that condensed in the solar nebula alongside the ices. The typical density of Kuiper Belt objects ranges from about 1 to 2 grams per cubic centimetre, compared to pure water ice at 0.92 grams per cubic centimetre and typical rocks at 3 to 4 grams per cubic centimetre. This suggests compositions of roughly 50 to 70% ice by mass, with the remainder being rocky materials. The largest objects may have differentiated, meaning denser rocky materials sank toward the centre, while lighter ices floated to the surface, creating a layered internal structure with a rock-rich core surrounded by an ice-rich mantle. Smaller objects likely remained undifferentiated, with rock and ice mixed throughout their interiors. Some Kuiper Belt objects show evidence of ammonia ice, which is particularly interesting because ammonia mixed with water forms a eutectic mixture that remains liquid at temperatures as low as 176 Kelvin, far colder than pure water's freezing point. This ammonia water liquid could have existed in Kuiper Belt object interiors early in their history, when radioactive decay provided heat and might have facilitated geological activity like cryovolcanism. The presence of ammonia might also explain some of the crystalline water ice observations, as ammonia water liquids erupting onto surfaces would freeze into crystalline form rather than amorphous ice. The inventory of materials in Kuiper Belt objects connects directly to questions about the origin of water and organic compounds on Earth. Some theories suggest that late-arriving comets and asteroids, some originating from the Kuiper Belt, delivered substantial amounts of water to the young Earth after it had cooled enough for oceans to persist. The organic compounds in these impactors might have provided raw materials for the chemistry that eventually led to life. While Earth's current water inventory is far too large to have come primarily from Kuiper Belt objects, these icy bodies might have contributed, and they certainly demonstrate that the outer solar system contains abundant water and organic material, resources that could potentially support human exploration and settlement in the distant future, or that might harbour life in subsurface oceans on the largest objects. The composition of these frozen worlds tells us not just about what they're made of, but about where they formed, what conditions existed in the outer solar nebula, how bodies evolved over billions of years under extreme cold, and what resources exist in the outer solar system. Each spectroscopic observation, each measurement of density or surface properties, adds to our understanding of these time capsules from the dawn of planetary formation. These archives of frozen chemistry that preserve, in molecular detail, the raw materials from which worlds are built. When astronomers observe Kuiper Belt objects through telescopes, measuring the intensity of reflected sunlight at different wavelengths, they discover a remarkable diversity of colours ranging from neutral grey to deep red, with some objects displaying subtle variations across their surfaces that hint at different compositional regions or geological processes. These colours aren't arbitrary, but rather encode information about surface composition, radiation exposure, collision history, and age, providing clues that help us understand not just individual objects, but the population as a whole. The study of Kuiper Belt object colours has become a sophisticated field where subtle differences in spectral properties reveal complex stories about how surfaces evolve in the radiation environment beyond Neptune. The reddest Kuiper Belt objects owe their colour to those organic compounds we call tholins, complex molecules built up over billions of years as cosmic rays and solar ultraviolet light process simple ices like methane into larger, more elaborate structures. The exact shade of red depends on the specific molecules present and how long the radiation processing has continued. Objects that have spent billions of years with methane-rich surfaces exposed to cosmic rays tend toward deeper, redder hues, while objects with younger or more frequently refreshed surfaces might appear less red or even neutral grey. This radiation processing happens slowly but relentlessly. Every cosmic ray that strikes a surface molecule has some probability of breaking chemical bonds and enabling new combinations to form, and integrated over millions or billions of years, the cumulative effect transforms surface chemistry substantially. Some Kuiper Belt objects appear much greyer or more neutral in colour, reflecting sunlight fairly evenly across visible wavelengths. These grey objects might have surfaces dominated by water ice, which is naturally white or grey, or they might be objects that have experienced recent geological activity that has resurfaced them with fresh material from the interior before tholins could build up. The colour difference between red and grey objects correlates somewhat with orbital properties. Classical Kuiper Belt objects, those on low inclination, low eccentricity orbits that have been minimally disturbed, tend toward redder colours, suggesting they've had billions of years of undisturbed radiation processing. Scattered disk objects and those in higher inclination orbits show more diversity, with both red and grey objects present, possibly indicating different collision histories or surface ages. Spectroscopic observations in infrared wavelengths, where different types of ice have characteristic absorption features, allow astronomers to identify specific materials on Kuiper Belt object surfaces. Water ice shows strong absorption at wavelengths around 1.5 and 2.0 microns. Methane ice has distinctive absorption features at 1.7, 2.2, and other wavelengths. When instruments on Earth-based telescopes or space observatories like the Hubble Space Telescope or James Webb Space Telescope measure these absorption patterns, they can determine not just that water or methane ice is present, but estimate how abundant it is and whether it's mixed with other materials or exists in relatively pure deposits. These spectroscopic observations have revealed that different Kuiper Belt objects have quite different surface compositions, with some dominated by water ice, others showing strong methane features, and still others displaying evidence for ammonia, carbon dioxide, or nitrogen ices. The presence of methane ice on an object's surface creates an interesting evolutionary cycle. Methane sublimes slowly even at Kuiper Belt temperatures, gradually escaping to space over millions of years. This should deplete surface methane over the age of the solar system, yet many objects still show methane absorption features, which suggests fresh methane is being supplied from subsurface reservoirs. This could happen through cryovolcanism, where subsurface liquids reach the surface and release dissolved gases, or through impacts that excavate fresh material from below, or even through seasonal cycles where methane condenses on the winter hemisphere and sublimes from the summer hemisphere, though this last mechanism requires objects with substantial atmospheres that can transport methane from one region to another. Color can also vary across a single object's surface, a phenomenon astronomers can detect when an object's brightness and color change slightly as it rotates, revealing different hemispheres to our view. Pluto displays dramatic color variations, with some regions dominated by reddish tholins, while other areas, particularly the nitrogen ice plains of Tombor Regio, informally called Sputnik Planitia, appear brighter and less red. These variations tell us about different geological processes active in different regions, about how volatile ices migrate and condense, about where impact craters have excavated fresh subsurface material, about the complex interplay of chemistry and geology that shapes these worlds despite their tiny size and extreme cold. The James Webb Space Telescope, with its powerful infrared capabilities, has begun revolutionizing our understanding of Kuiper Belt, object compositions, and surface properties. Its sensitivity and spectral resolution allow detection of absorption features from minor constituents that previous instruments couldn't reliably identify. Early observations have confirmed carbon dioxide ice on some objects, detected ethane on others, and revealed subtle spectral features that help constrain mixing ratios and ice grain sizes. As Webb continues observing Kuiper Belt objects over the coming years, the census of compositions and colors will grow increasingly detailed, allowing astronomers to test formation models, understand how surfaces evolve, and perhaps identify objects with unusual or unique compositions that merit priority for future spacecraft missions. The diversity of colors in the Kuiper Belt reminds us that even in this frozen realm, no two worlds are exactly alike. Each object has its own history of formation, its own sequence of collisions and heating events, its own exposure to cosmic rays and ultraviolet light, all of which combine to create the specific hue we observe when photons that traveled 4 or 5 billion kilometers from the Sun bounced off an icy surface and traveled another 4 or 5 billion kilometers to our telescopes. Those photons carry information encoded in their wavelengths, information about molecules on surfaces we may never visit, worlds we may never see up close, but which we can nonetheless understand through the patient analysis of light, that universal messenger that connects us to every object in the cosmos, no matter how distant or small. The environment of the Kuiper Belt exists at temperatures so cold they challenge our everyday intuition about how materials behave, where substances that flow as liquids on Earth become harder than steel, and where the subtle quantum mechanical properties of matter begin to manifest in ways they never could at higher temperatures. Understanding the physics of this extreme cold requires thinking about temperature not as we experience it subjectively, but as a measure of molecular kinetic energy, the average speed at which atoms and molecules vibrate and move. At 40 Kelvin, the typical temperature in the Kuiper Belt, that kinetic energy is less than 1% of what it is at room temperature. And this changes virtually everything about how materials behave. Water ice at 40 Kelvin becomes an entirely different material than the ice we encounter in our freezers or during winter. Its mechanical properties resemble rock more than ice, with similar hardness, compressive strength, and rigidity. Where ice at 273 Kelvin, just below freezing, can deform slowly under pressure, flowing like a very viscous fluid over hours or days. Water ice at 40 Kelvin is brittle and fractures like glass when stressed. This has implications for the geology of Kuiper Belt objects. Any mountains made of water ice won't slump or flow over time the way glaciers do on Earth. They'll remain standing for billions of years, supported by the structural strength of ice that's cold enough to behave like granite. The impact craters that form when smaller bodies collide with Kuiper Belt objects will preserve their shapes indefinitely, without the relaxation and modification that happens on warmer worlds, where ice can flow and deform. At these temperatures, many substances that we think of as gases exist as solid ices with distinctive properties. Nitrogen, which makes up 78% of Earth's atmosphere, freezes at 63 Kelvin at atmospheric pressure, and in the vacuum of space with essentially no pressure, it remains solid even at temperatures as high as 50 or 60 Kelvin. Nitrogen ice has very low viscosity even when solid, allowing it to flow slowly like a glacier, filling in low-lying areas and creating smooth plains. This is exactly what New Horizons observed on Pluto, where nitrogen ice dominates the smooth heart-shaped region and shows evidence of convective overturn, with warmer nitrogen from below rising to the surface, while cooler nitrogen sinks, creating a slow circulation pattern similar to convection in Earth's mantle, but happening in solid nitrogen ice rather than rock. Methane, carbon monoxide, and nitrogen can mix together in various proportions, creating solid solutions where molecules of different types are randomly mixed in a single crystalline structure. The exact properties of these mixtures depend on temperature and composition. At slightly warmer temperatures, or on objects with more sunlight absorption, these volatile ices can sublime, turning directly from solid to gas without passing through a liquid phase. This sublimation can drive atmospheric activity, creating thin, temporary atmospheres around larger Kuiper Belt objects when sunlight warms the surface enough to vaporize ices. These atmospheres are incredibly tenuous, with surface pressures millions of times lower than Earth's atmosphere, but they're substantial enough to transport molecules from one region to another, to create hazes of organic particles, and to slowly escape to space over time, carrying away the lightest molecules that reach sufficient velocity to overcome the weak gravity of these small worlds. The concept of cryovolcanism, volcanic activity driven not by molten rock but by melting ice, becomes relevant on larger Kuiper Belt objects that might retain internal heat from radioactive decay. If the interior of an object like Pluto or Eris contains enough radioactive elements, particularly long-lived isotopes like uranium-238, thorium-232, and potassium-40, the heat generated by their decay might keep subsurface regions warmer than the surface. In the presence of ammonia, which acts as an antifreeze for water ice, temperatures above 176 Kelvin could allow liquid water-ammonia mixtures to exist at depths of tens or hundreds of kilometers. If this liquid finds paths to the surface, perhaps through cracks created by impacts, or through differential expansion and contraction, it could erupt as a cryovolcanic flow, quickly freezing when exposed to surface temperatures, but creating fresh, relatively young terrain that hasn't experienced billions of years of radiation processing. The thermal conductivity of materials at Kuiper Belt temperatures affects how quickly heat can be transported from one region to another. Ice has relatively low thermal conductivity, meaning it acts as a good insulator. An object with internal heat sources will develop a temperature gradient with warmer interior and colder surface, and the steepness of this gradient depends on how efficiently heat can conduct outward. For large objects, this temperature difference can be substantial, potentially allowing liquid water or water-ammonia oceans to exist at depth even when surface temperatures are at 40 Kelvin. These subsurface oceans, if they exist, could potentially harbour life, though the energy available to drive biological processes would be minimal, and any such life would need to operate on extremely slow timescales, perhaps taking centuries or millennia to accomplish what terrestrial microbes might do in days. The interaction of matter with radiation takes on special character at these extreme temperatures. Cosmic rays, high-energy particles, mostly originating from supernova explosions throughout the galaxy, constantly bombard Kuiper Belt objects, penetrating the top few meters of surface material and breaking chemical bonds as they pass through. Ultraviolet light from the sun, though much weaker at these distances, also contributes to radiation processing. At temperatures around 40 Kelvin, molecules that have been broken apart or ionized by radiation move very slowly and might remain separated for long periods before finding new bonding partners. This allows unusual molecular species and radicals to persist much longer than they could at higher temperatures, potentially creating unique chemistry that we don't observe anywhere else in the solar system. As you drift deeper into sleep, imagine the physics of these frozen worlds, where molecular motion has nearly ceased, where substances we think of as fluids have become solid as stone, where time seems to slow down along with atomic vibrations, where change happens on geological timescales measured in billions of years rather than the rapid pace we experience in our daily lives. The extreme cold of the Kuiper Belt creates a realm where the normal rules of chemistry and physics still apply, but produce results so different from our everyday experience that understanding them requires careful thought and mathematical precision, where the patient work of scientists using quantum mechanics and thermodynamics reveals how nature behaves at the edge of absolute zero. In the twilight between stars, where temperature asymptotically approaches but never quite reaches the ultimate cold, where all thermal motion would cease. On July 14, 2015, after a journey of 9.5 years covering more than 5 billion kilometers, NASA's New Horizons spacecraft passed within 12,500 kilometers of Pluto's surface, traveling at 14 kilometers per second, too fast to orbit or slow down, but perfect for a reconnaissance flyby that would revolutionize our understanding of Kuiper Belt objects. The images and data transmitted back to Earth over the following months revealed a world far more complex, active, and beautiful than anyone had anticipated. A frozen landscape of nitrogen glaciers, water ice mountains rising 5 kilometers high, atmospheric hazes extending hundreds of kilometers into space, and surface features suggesting geological activity within the past few million years, impossibly young for a world orbiting in the deep freeze beyond Neptune for 4.6 billion years. The heart-shaped region that quickly captured public imagination, informally named Tombor Regio after Pluto's discoverer, dominated the encounter hemisphere. Its western lobe, called Sputnik Planitia, appeared as a vast plain of smooth nitrogen ice, stretching roughly 1,000 kilometers across, divided into polygonal cells tens of kilometers wide that suggested convective overturn. Scientists realized they were looking at a geological process similar to convection in Earth's mantle or in boiling water, except happening in solid nitrogen ice over timescales of hundreds of thousands of years. Warmer nitrogen from a few kilometers depth, warmed by perhaps half a degree from heat escaping Pluto's interior or from slight compression at depth, rises slowly to the surface while cooler surface nitrogen sinks, creating a circulation pattern that continuously renews the surface and explains why Sputnik Planitia shows no impact craters, despite being exposed to meteoroid bombardment for potentially billions of years. Surrounding this nitrogen ice plain, New Horizons imaged mountain ranges of water ice rising kilometers above the surrounding terrain. At Pluto's temperature, water ice has the strength of rock and can support substantial topographic relief without slumping or flowing. These mountains, given informal names like Norgay Montes and Hillary Montes after Everest summiteers, appeared bright and relatively crater-free, suggesting they too are geologically young, perhaps less than 100 million years old. The mechanism that created them remains debated. They might represent blocks of water ice crust that floated upward in denser nitrogen ice, similar to icebergs floating in water, or they might have been thrust upward by tectonic forces as Pluto's interior cooled and contracted over geological time, or they might relate to the unusual orbital dynamics of Pluto and Charon that create tidal stresses in Pluto's interior. The diversity of terrains observed across Pluto's surface exceeded all predictions. dark, heavily cratered regions suggested ancient surfaces billions of years old, preserved with minimal modification. Smooth plains at various locations indicated resurfacing by either cryovolcanism or glacial flows. Networks of troughs and ridges hinted at extensional tectonics, where the crust had been pulled apart. Exotic features like the regularly spaced, blade-like ridges of Tartarus Dorsa region, aligned north-south and hundreds of meters tall, suggested erosional processes where methane ice preferentially sublimates from certain orientations, leaving behind harder water ice ridges, a phenomenon that might be unique to Pluto's specific geometry and obliquity, which cause unusual patterns of sunlight and shadow. Pluto's atmosphere, detected from Earth through stellar occultations, but never directly imaged before New Horizons, appeared as beautiful layers of bluish haze extending up to 200 kilometers altitude. This atmosphere, composed primarily of nitrogen, with traces of methane and carbon monoxide, escapes into space at a rate of thousands of tons per day, though Pluto's mass is large enough that this escape will continue for billions of years before significantly depleting the surface ice reservoirs. The hazes form when ultraviolet light breaks apart methane molecules high in the atmosphere, allowing the fragments to combine into more complex organic molecules that aggregate into tiny particles. These particles, similar to the tholins we discussed earlier, eventually settle onto Pluto's surface, contributing to the reddish color seen in some regions and to the slow accumulation of complex organic material that has been building up over the age of the solar system. Pluto's largest moon, Charon, revealed its own surprises during the New Horizons encounter. A massive canyon system stretched across Charon's equator, perhaps 1,000 kilometers long and 9 kilometers deep, suggesting that Charon's interior had frozen and expanded, cracking the surface in the process. The North Polar region displayed unusual reddish coloring, possibly from tholins that formed when gases escaping from Pluto migrated to Charon and became trapped in the colder polar regions. Charon's generally grey colour and lack of obvious volatile ices suggested a surface dominated by water ice, consistent with Charon's lower mass and weaker gravity, that would have allowed it to lose lighter ices early in its history. 4 years after the Pluto encounter, on January 1st, 20, New Horizons performed another flyby, this time of a much smaller and more distant object initially designated 2014 MU69 and later officially named Arakoth, meaning sky in the Powhatan language. Arakoth, orbiting at about 44 astronomical units in the classical Kuiper Belt, appeared as a contact binary, 2 lobes gently merged together, each one roughly 20 kilometers across. Its smooth surface, reddish color, and lack of large craters suggested it formed through the gentle merger of 2 separate objects early in solar system history, an example of how planetesimals grew through accretion. Unlike Pluto with its complex geology, Arakoth appeared relatively pristine and simple, a frozen remnant from the era of planet formation that had experienced minimal subsequent evolution. The data from New Horizons continues to be analysed years after the encounters, with new papers regularly reporting discoveries about Pluto's atmosphere, surface composition, geological history, and orbital dynamics. The mission demonstrated that even small, cold worlds in the outer solar system can be geologically active and morphologically diverse, that our theoretical models before the encounter had underestimated the complexity that awaited, and that each Kuiper Belt object likely has its own unique story to tell. The success of New Horizons has inspired proposals for future missions to other Kuiper Belt objects, perhaps an orbiter that could study seasonal changes and atmospheric dynamics over multiple orbits, or a lander that could directly sample surface materials and search for organic chemistry that might be relevant to the origins of life. Here on Whispering Universes, we recognize New Horizons as one of the great exploration missions of our era, expanding the frontier of human knowledge to regions that had existed only as points of light in our telescopes, revealing worlds of wonder at the edge of sleep. Beyond Pluto and Arakoth, the Kuiper Belt contains several other large objects classified as dwarf planets, each one revealing unique characteristics that expand our understanding of what frozen worlds can be like in the outer solar system. These objects, discovered between 2003 and 2005 during intensive survey programs, have been studied primarily through Earth-based telescopes and space observatories. Their properties inferred from brightness, colour, spectroscopy, and in some cases from observations of moons that allow mass determination. While we await future missions that might visit them directly, the diversity already apparent tells us that Kuiper Belt objects follow different evolutionary paths depending on their size, composition, formation location, and subsequent history. Eris, discovered in 2005 by Mike Brown's team at Caltech, orbits at an average distance of 68 astronomical units from the Sun on a highly elliptical orbit that takes it from 38 to 98 astronomical units over its 560-year orbital period. Its orbit is also steeply inclined, tilted 44 degrees relative to the plane of the planets, marking it as a member of the scattered disk population that has been strongly perturbed by gravitational interactions with Neptune. Eris is slightly smaller than Pluto in diameter, about 2,126 kilometers compared to Pluto's 2,377 kilometers, but it's significantly more massive, suggesting a higher density and a composition with more rock relative to ice than Pluto contains. Spectroscopic observations reveal a surface dominated by bright, reflective methane ice, giving Eris an albedo close to 0.96, meaning it reflects 96% of incident sunlight, making it one of the most reflective objects in the solar system, brighter even than fresh snow on Earth. The presence of so much fresh methane ice on Eris's surface poses an interesting question, as methane should slowly sublime away even at Eris's current cold temperature. The answer might lie in Eris's highly elliptical orbit. When Eris approaches closest to the Sun, its temperature rises enough that methane sublimes from the surface, forming a temporary thin atmosphere. As Eris moves back toward its distant aphelion, the temperature drops and the atmospheric methane freezes back onto the surface as fresh bright ice. This cycle of sublimation and condensation might continuously refresh Eris's surface, keeping it bright and crater-free. Alternatively, Eris might have experienced a large impact in the relatively recent past that excavated fresh methane ice from the interior, though the probability of such an impact, during the tiny fraction of solar system history we happen to be observing, seems low. Makemake, the third largest known Kuiper Belt object with a diameter of about 1,130 kilometers, orbits at 46 astronomical units in a classical Kuiper Belt orbit with relatively low eccentricity but inclination of 29 degrees. Spectroscopic observations show a surface rich in methane ice, nitrogen ice, and complex organic compounds, giving it a slightly reddish hue, though not as red as some smaller Kuiper Belt objects. Makemake is bright enough that Hubble Space Telescope observations can resolve its disk, allowing direct measurement of its size. For years, Makemake was thought to be without moons, making mass determination difficult, but in 2016, astronomers discovered a small, dark moon orbiting Makemake at a distance of about 21,000 kilometers with an orbital period of roughly 12 days. This moon, informally called MK2, allowed mass calculation, showing Makemake has a density of about 1.7 grams per cubic centimeter, consistent with a mix of rock and ice. Observations attempting to detect an atmosphere around Makemake have yielded mostly null results, suggesting that, unlike Pluto, Makemake either lacks a significant atmosphere or has one so tenuous it's undetectable with current techniques. This could be because Makemake is slightly smaller and colder than Pluto, making volatile retention more difficult, or because Makemake's surface composition differs in ways that affect atmospheric production and loss. The absence of an obvious atmosphere, combined with surface spectroscopy showing methane ice, suggests that methane must be quite cold and stable on Makemake's surface, subliming very slowly, if at all, under current conditions. Haumea stands out as perhaps the strangest dwarf planet we've discovered, a rapidly rotating, elongated object that challenges our assumptions about what large bodies in the outer solar system should look like. Haumea orbits at about 43 astronomical units with moderate eccentricity, and it completes one rotation every 3.9 hours, faster than any other large object in the solar system. This rapid rotation has deformed Haumea into an ellipsoidal shape, roughly 2,000 by 1,600 by 1,000 kilometers, making it look more like a rugby ball than a sphere. The reason for this extreme rotation likely traces back to a giant impact early in Haumea's history, a collision energetic enough to spin up the body and excavate a substantial portion of its outer ice mantle, leaving behind a body with higher density than typical Kuiper Belt objects, around 2.6 grams per cubic centimetre, suggesting a composition that's perhaps 70% rock by mass. Even more remarkable, Haumea possesses a ring system, discovered in 2017 through observations of stellar occultations, where Haumea passed in front of a background star, and astronomers measured how the star's light dimmed. The ring orbits Haumea's equator at a distance of about 200-300 kilometers from Haumea's center, right at the 3:1 resonance with Haumea's rotation, meaning particles in the ring complete 3 orbits for every rotation of Haumea. The ring is narrow, perhaps only 70 kilometers wide, and its origin remains uncertain. It might consist of debris from that ancient giant impact, material that was ejected but didn't escape entirely, instead spreading into a ring. Or it might have formed from the collision of 2 of Haumea's moons, which themselves might be fragments from the original impact. Haumea has 2 known moons, Hi'iaka and Namaka, both much smaller than their parent, and both likely fragments from the giant impact that shaped Haumea. Spectroscopy shows these moons have water ice surfaces similar to Haumea's, supporting the impact fragmentation scenario. The entire Haumea system, the elongated primary, the 2 moons, and the ring, represents a collision family in the Kuiper Belt, remnants of a violent event that redistributed mass and angular momentum billions of years ago. Interestingly, astronomers have identified several other Kuiper Belt objects with similar spectral properties and orbital characteristics that might be additional fragments from the same collision, ejected with enough velocity to escape Haumea's gravity and enter independent orbits. Quaoar, another large Kuiper Belt object about 1,110 kilometers in diameter, orbiting at 43 astronomical units, made headlines in 2023 when astronomers announced the discovery of a ring system orbiting well outside the Roche limit, the distance within which tidal forces would normally destroy rings by pulling particles apart. This discovery challenged conventional understanding of where rings can exist and suggested that some special property of the ring particles, perhaps their low collisional velocities or specific composition, allows them to survive where theory suggested they shouldn't. Quaoar also has a small moon named Waywat, about 170 kilometers across, orbiting at 14,000 kilometers distance. These diverse dwarf planets demonstrate that size isn't destiny in the Kuiper Belt. Objects of similar mass can have very different properties depending on their formation circumstances, collision histories, and orbital evolution. Some, like Eris and Makemake, have bright, methane-rich surfaces that reflect most incident light. Others, like Haumea, have darker water ice surfaces and unusual shapes from ancient impacts. Some have substantial moon systems, while others orbit alone. Some might have thin atmospheres, while others show no atmospheric signature. Each one is a scientific target worthy of detailed study, a world with its own geology, chemistry, and history waiting to be explored by future missions that might visit these distant frozen realms and reveal details we can barely glimpse from Earth. The moons orbiting Kuiper Belt objects provide crucial information about the masses, densities, and formation histories of their parent bodies, while also telling their own stories of creation, evolution, and survival in the harsh environment beyond Neptune. Discovering these moons requires patience and powerful telescopes, as they're typically small, dark, and located very close to much brighter primary bodies. The Hubble Space Telescope has been instrumental in finding moons around distant Kuiper Belt objects, its sharp imaging allowing separation of faint moonlight from the glare of the primary. Ground-based telescopes using adaptive optics, which corrects for atmospheric blurring in real time, have also contributed to the census. As of our current accounting, astronomers have discovered moons around several dozen Kuiper Belt objects, and this number continues to grow as observational techniques improve. The Pluto-Charon system represents the most studied example, a binary where both objects orbit a common center of mass, or barycenter, located in the space between them rather than inside either body. Charon, with about 1/8 of Pluto's mass and roughly half its diameter, is unusually large relative to its primary, more similar to the Earth-Moon system than to the relationships between most planets and their satellites in the solar system. The two objects are tidally locked to each other, meaning Pluto always shows the same face to Charon, and vice versa, each one frozen in mutual gravitational embrace with their rotation periods equal to their 6.4-day orbital period. This tidal locking happened relatively early in their history, as tidal forces dissipated energy from the system, gradually synchronizing rotation and orbit. The formation of the Pluto-Charon system almost certainly involved a giant impact, an event where a large body, perhaps 1/3 to a half the mass of Pluto, collided with proto-Pluto when the solar system was young, and such collisions were still common. The impact would have been catastrophic, but not quite head-on, delivering a glancing blow that ejected substantial material into orbit around Pluto. This debris, heated by the impact and mixed from both the impactor and target, gradually accreted into Charon, and possibly the smaller outer moons as well. The giant impact scenario explains Charon's unusually large size relative to Pluto, the system's high angular momentum, and the composition of Charon, which differs slightly from Pluto's in ways consistent with formation from mixed impact debris. Pluto's 4 smaller moons, Styx, Nix, Kerberos, and Hydra, orbit beyond Charon at distances ranging from about 42,000 to 65,000 kilometers from Pluto. These moons are tiny, ranging from roughly 10 to 50 kilometers across, and they're remarkably bright, reflecting 40% to 50% of incident sunlight, suggesting surfaces dominated by relatively clean water ice. Their orbits lie close to the plane of Pluto's equator and near simple resonances with Charon's orbit, strong evidence that they formed from the same impact debris that created Charon, representing smaller accumulations in the outer disk of material. New Horizons images showed these moons have irregular, elongated shapes, as expected for small bodies where gravity is too weak to pull them into spheres. The orbital dynamics of these small moons might be chaotic, meaning their specific positions in their orbits evolve unpredictably over time, even though the overall orbital shapes remain stable. This chaos arises from the complex gravitational interactions between Pluto, Charon, and the small moons, where small perturbations can amplify over time in ways that make long-term prediction impossible. Despite this orbital chaos, the system has remained stable for billions of years, and the small moons will likely continue orbiting Pluto indefinitely, unless some rare event like a close encounter with another Kuiper Belt object disrupts the system. Other large Kuiper Belt objects also host moons, though typically these satellites are much smaller relative to their primaries than Charon is to Pluto. Eris has one known moon, Haumea, about 700 kilometers in diameter, orbiting at 37,000 kilometers distance with a 16-day period. Observations of Haumea's orbit allowed the first accurate measurement of Eris's mass, revealing that Eris is more massive than Pluto, despite being slightly smaller in diameter. Haumea's two moons, Haumea and Makemake, orbit at distances of 50,000 and 39,000 kilometers respectively, both likely fragments from the giant impact that shaped Haumea and created its rapid rotation. Makemake's small moon Mk2, discovered only recently, orbits at about 21,000 kilometers and appears quite dark compared to Makemake itself, possibly because it's smaller and lost volatile ices more easily, leaving behind darker refractory material. The frequency of binary and multiple systems in the Kuiper Belt exceeds what we see in the asteroid belt, with perhaps 10% to 20% of classical Kuiper Belt objects having detected moons. This high binary fraction might relate to how these objects formed, through gentle mergers and captures in a relatively dense early disk, or to a population of objects that formed as binaries directly from the solar nebula. Some small Kuiper Belt objects exist as contact binaries, like Arakoth, where two lobes are gently touching, possibly representing an intermediate stage between a binary system with two separated components and a single merged object. The diversity of satellite systems tells us that collisions, captures, and dynamical interactions were common in the early Kuiper Belt, and that each system's satellite configuration preserves information about these ancient events. Studying the orbits of these moons allows astronomers to measure masses with high precision, which when combined with size measurements gives densities, crucial information for understanding composition and internal structure. Monitoring how moons perturb each other's orbits reveals additional details about mass distribution within the system. Observing how moons interact with rings, as in the Haumea system, illuminates gravitational dynamics at work in exotic environments. And searching for additional small moons around known Kuiper Belt objects continues to refine our census, each new detection adding to our understanding of how these frozen worlds interact gravitationally, how they formed from the solar nebula, and what collisional and dynamical processes have shaped them over the age of the solar system. The moons of the Kuiper Belt, small and dark as they are, serve as gravitational laboratories where we can study fundamental physics, playing out over cosmic distances and timescales. Silent witnesses to events that happened billions of years ago in the twilight realm at the edge of our solar system. The Kuiper Belt isn't a static population of objects forever orbiting in their distant realm, but rather a dynamically active region that regularly sends smaller bodies sunward, creating the short-period comets that grace our skies and occasionally impact planets, delivering water, organic compounds, and perhaps even the chemical precursors necessary for life. Understanding the connection between the Kuiper Belt and comets helps us trace the origins of these spectacular visitors and recognize that the frozen worlds we've been discussing aren't isolated from the inner solar system, but are connected to us through gravitational pathways that have existed since the planets formed. Short-period comets, defined as those with orbital periods less than 200 years, show strong dynamical connections to the Kuiper Belt. Their orbits typically have low inclinations relative to the plane of the planets, exactly what we'd expect if they originated from a disk-like source rather than a spherical distribution. The most famous short-period comet, 1P Halley, completes an orbit every 76 years, travelling from just inside Earth's orbit at perihelion to beyond Neptune's orbit at aphelion. Other well-known short-period comets include 2P Encke, which orbits every 3.3 years, and 67 Churyumov-Gerasimenko, the comet visited by ESA's Rosetta spacecraft, which orbits every 6.5 years. These comets appear in our skies because gravitational interactions in the Kuiper Belt and scattered disk occasionally perturb objects onto planet-crossing orbits. The mechanism typically begins in the scattered disk, where objects on highly elliptical orbits occasionally pass close enough to Neptune to receive gravitational kicks that change their trajectories. Most such encounters result in ejection from the solar system entirely or return to distant scattered disk orbits, but occasionally an object receives just the right perturbation to send it sunward with a trajectory that brings it into the inner solar system. Once in this region, the object becomes subject to gravitational influences from Jupiter, Saturn, and the other planets, which can further modify its orbit through repeated encounters. Some objects gain enough energy to escape, while others have their orbits circularized into shorter period paths that bring them repeatedly through the inner solar system as observable comets. The transition from Kuiper Belt object to active comet happens when these bodies approach close enough to the Sun that surface temperatures rise above the sublimation point for volatile ices. For water ice, this occurs at about 3 astronomical units, beyond the asteroid belt but inside Jupiter's orbit. As ices sublime, they carry dust particles with them, creating the characteristic coma, that fuzzy cloud of gas and dust surrounding the nucleus, and the spectacular tails that always point away from the Sun due to radiation pressure and solar wind. Active comets lose mass with each perihelion passage. Water sublimates away, organics and dust are shed, and eventually, after perhaps hundreds or thousands of orbits, depending on the comet's size and perihelion distance, the volatile ices are depleted and the object becomes dormant, appearing more like an asteroid than a comet. Between the Kuiper Belt and the orbits of the giant planets lies a transitional population called centaurs, objects that have been scattered inward from the Kuiper Belt but haven't yet reached short-period comet orbits. Centaurs typically orbit between Jupiter and Neptune, with some showing cometary activity when they pass close enough to the Sun for ices to sublime. The most famous centaur is 2060 Chiron, about 200 kilometers in diameter, which orbits between Saturn and Uranus with a period of about 50 years. Chiron shows sporadic cometary activity, developing a faint coma when near perihelion, demonstrating the transitional nature between inert Kuiper Belt object and active comet. Other large centaurs include 199 Chariklo, which possesses a ring system, and 5145 Pholus, which shows one of the reddest colours of any solar system object, suggesting a surface rich in complex organic tholins. The centaur population is dynamically unstable on timescales of millions of years. Gravitational interactions with the giant planets will eventually either eject these objects from the solar system or send them into the inner solar system, where they become Jupiter family comets. Current population estimates suggest several thousand centaurs larger than 1 kilometer in diameter, with a steady-state balance between new objects arriving from the scattered disk and existing objects being removed through ejection or transition to shorter period orbits. Observationally, centaurs provide the best opportunity to study recently arrived Kuiper Belt objects, as they're much closer and brighter than objects still in the Kuiper Belt proper, allowing detailed spectroscopic characterization of surface composition and monitoring of activity onset as they approach the Sun. Some objects from the Kuiper Belt reach Earth's vicinity and occasionally impact our planet, delivering extraterrestrial material that we can study in laboratories with far greater precision than possible through remote observation. Meteorites derived from comets are rare in our collections, as most cometary material is fragile and tends to burn up completely in the atmosphere or fragment into dust that settles slowly rather than creating recoverable meteorite falls. However, some meteoritic material likely has cometary origins. An analysis of dust collected during comet encounters or captured in Earth's stratosphere has revealed that cometary composition includes complex organic molecules, water ice, and refractory materials that provide ground truth calibration for remote spectroscopic observations of Kuiper Belt objects. The possibility that comets delivered substantial amounts of water and organic compounds to early Earth, contributing to the inventory available for the origin of life, makes Kuiper Belt objects relevant to astrobiology and our understanding of how life began on our world. While debate continues about how much of Earth's water came from comets versus asteroids versus was incorporated during Earth's formation, isotopic analysis of water in comets from various sources suggests at least some contribution. Similarly, the complex organic molecules found in comets, including amino acids detected in samples from comet Wild 2 returned by NASA's Stardust mission, demonstrate that Kuiper Belt objects contain chemical building blocks relevant to biology. Whether these materials were essential for life's origin or merely supplementary to terrestrial chemistry remains an open question, but the connection exists and reminds us that the frozen worlds at the edge of the solar system aren't disconnected from our own world, but are linked through billions of years of cosmic delivery, through meteoritic falls and cometary impacts that brought materials from the outer reaches of the solar nebula to Earth's surface, where chemistry and evolution eventually produced the biosphere we see today. The flux of Kuiper Belt objects entering the inner solar system has varied throughout Earth's history, driven by changes in the giant planet's orbits and by perturbations from passing stars when our sun was younger and still relatively near its birth cluster. Periods of enhanced cometary impacts might have influenced Earth's climate, its delivery of volatiles, and possibly even evolutionary history through impacts large enough to cause mass extinctions or environmental changes. The bombardment continues today at lower rates, with occasional bright comets appearing in our skies, reminders of the deep connection between Earth and the frozen frontier, between the comfortable realm we inhabit and the twilight zone where sunlight fades to starlight, and ancient ices preserve the chemical fingerprints of the solar nebula from which everything we know emerged. In 2016, astronomers Konstantin Batygin and Mike Brown published a paper suggesting that the orbits of several extremely distant solar system objects showed peculiar clustering that couldn't easily be explained by random chance or by the known gravitational influences of the giant planets. These objects, with orbits that take them hundreds of astronomical units from the Sun at their most distant points, all seem to have their closest approaches to the Sun, their perihelia, clustered in one general direction, and their orbital planes tilted in similar ways. Batygin and Brown calculated that the probability of this clustering occurring randomly was less than 1%, and they proposed an explanation. An as yet undiscovered planet, perhaps 5 to 10 times Earth's mass, orbiting at several hundred astronomical units from the Sun, its gravity shepherding these distant objects into their observed orbital configuration. They dubbed this hypothetical world Planet 9, and its possible existence has sparked an ongoing search that continues today. The evidence comes from careful mapping of the most distant Kuiper Belt and scattered disk objects, those with semi-major axes greater than about 250 astronomical units and perihelia beyond Neptune's gravitational influence at about 30 astronomical units. The sample includes objects like Sedna, discovered in 2003, which orbits with perihelion at 76 astronomical units and aphelion near 900 astronomical units, taking about 11,000 years to complete one orbit. Other extreme members include 2012 VP113, 2015 TG387, and several additional objects found by deep survey programs. When astronomers plotted the orbital parameters of these objects, the clustering became apparent, not in their current positions, which are randomly distributed as expected for objects on such long-period orbits, but in the orientations of their orbits, the directions their ellipses point, and the tilts of their orbital planes relative to the ecliptic. Computer simulations support the Planet 9 hypothesis. When researchers model the orbital evolution of distant scattered disk objects under the gravitational influence of the known giant planets, plus a hypothetical massive planet in a distant eccentric orbit, the simulations naturally produce the kind of clustering observed. The mechanism involves a process called orbital resonances and secular perturbations, where the distant planet's gravity, acting over millions of years, gradually organizes the orbits of smaller bodies into preferred configurations. The simulations also make predictions about where such a planet should currently be located in its own orbit, narrowing the search region to specific patches of sky where deep surveys might detect its reflected sunlight. However, finding Planet 9, if it exists, presents extraordinary observational challenges. At a distance of perhaps 400 to 800 astronomical units, depending on where it currently is in its orbit, such a planet would be extremely faint, perhaps magnitude 22 to 24, fainter than all but the deepest surveys routinely reach. It would also move very slowly against the background stars, taking hundreds or thousands of years to complete one orbit, meaning its motion over days or weeks would be tiny and difficult to detect without very precise position measurements. The search area covers thousands of square degrees of sky, and distinguishing a single slow-moving point of light from millions of background stars and galaxies requires automated detection algorithms and careful follow-up observation of candidates. Several survey programs, including searches using the Subaru telescope in Hawaii and analysis of data from NASA's Wide Field Infrared Survey Explorer-WISE satellite, have been systematically examining the predicted search regions, so far without confirmed detection. Alternative explanations for the orbital clustering have been proposed, ranging from collective gravitational effects from the entire Kuiper Belt acting coherently to observational biases where astronomers have preferentially discovered objects in certain orbital configurations, making the clustering appear stronger than it really is, to the possibility that a passing star in our Sun's distant past perturbed these orbits into their current configuration. Each alternative has its proponents and its problems. The collective gravity explanation requires the Kuiper Belt to be much more massive than current estimates suggest, by factors of 10 or more, which seems inconsistent with other constraints on the total mass in the outer solar system. The observational bias explanation struggles to fully account for the clustering once careful statistical analysis accounts for survey detection efficiencies. The passing star scenario could explain some features, but requires fine-tuning the encounter parameters to match observations. The discovery of additional, extreme distant objects continues to refine the evidence, either for or against Planet 9. Each new detection adds one more data point to the statistical sample, either strengthening the clustering signal or diluting it if new objects have random orbital orientations. As of today, the sample includes fewer than 20 objects meeting the strict criteria for inclusion. Enough to suggest something interesting, but not enough to be conclusive. Future discoveries from surveys like the Vera C. Rubin Observatory's Legacy Survey of Space and Time, which will begin operations in the mid-2020s and will be capable of detecting fainter objects across larger areas of sky than any previous survey, should substantially increase the sample size and either confirm the clustering or show it was a statistical fluctuation. If Planet 9 exists, its origin poses fascinating questions. It might be a core of a failed giant planet that formed in the inner solar system, along with Jupiter, Saturn, Uranus, and Neptune, but was ejected to a distant orbit through gravitational interactions during the era of planetary migration. Alternatively, it could be a rogue planet captured from interstellar space during the Sun's time in its birth cluster, an interloper that became gravitationally bound to our solar system. Its composition would likely resemble Uranus and Neptune, with a rock ice core surrounded by a substantial envelope of hydrogen and helium, though much reduced compared to Jupiter or Saturn. At several hundred astronomical units from the Sun, surface temperatures would be around 40 Kelvin, similar to typical Kuiper Belt temperatures, cold enough that even hydrogen and helium might be partially frozen, or at least supercooled. The search for Planet 9 represents a return to the classic astronomical hunt for unknown planets through their gravitational influences. The same technique that led to Neptune's discovery in 1846, when astronomers noticed Uranus's orbit was being perturbed by something unseen. That search succeeded in part because Neptune is relatively large and close, making its gravitational effect strong, and its eventual detection straightforward once observers knew where to look. Planet 9, if it exists, presents a far more difficult challenge, orders of magnitude fainter and more distant, requiring modern sky surveys and computational power to sift through enormous data sets, looking for that one point of light moving slightly against the stellar background. The quest continues, astronomers patiently examining images, checking candidates, refining orbital models, all in hopes of extending the census of planets to include one more major world in the outer darkness, a frozen giant shepherding the most distant objects at the very edge of our solar system's gravitational reach, orbiting where the Sun appears as little more than the brightest star in a black sky filled with galaxies and stellar clouds at the boundary between what belongs to our Sun and what belongs to the wider Milky Way. The Kuiper Belt's greatest value to planetary science lies in its role as a museum of solar system formation, a preserved sample of the protoplanetary disk that existed 4.6 billion years ago, when planets were still forming and the chemistry of the solar nebula was being locked into solid bodies. Unlike the terrestrial planets, where geological activity has recycled and processed original materials beyond recognition, or the giant planets, where we cannot directly sample formation materials, beneath thick atmospheres, Kuiper Belt objects have remained largely frozen and unmodified since they formed, their compositions and physical properties encoding information about conditions in the outer solar nebula that we can read with sophisticated instruments and careful analysis. The isotopic composition of materials in Kuiper Belt objects provides particularly powerful constraints on formation conditions. Isotopes are versions of the same element with different numbers of neutrons in their nuclei, and the ratios of different isotopes in a sample depend on the temperature, pressure, and chemical processes that occurred when those materials formed. For example, the ratio of deuterium, heavy hydrogen with one proton and one neutron, to normal hydrogen with just one proton varies depending on temperature during formation, with cold conditions favouring higher deuterium enrichment. Measurements of deuterium to hydrogen ratios in water from comets originating in the Kuiper Belt can thus tell us about the temperature in the outer solar nebula when water ice condensed. Early measurements suggested cometary water had deuterium enrichment significantly higher than Earth's ocean water, leading to suggestions that comets contributed relatively little to Earth's water inventory. However, more recent measurements from Rosetta spacecraft observations of comet 67P Churyumov-Gerasimenko showed deuterium to hydrogen ratios much closer to terrestrial values, indicating that comets from different source regions in the Kuiper Belt might have formed under different conditions and have differences at different isotopic signatures. This diversity tells us that the outer solar nebula wasn't uniform, but had temperature and composition gradients, with materials at different distances and different times incorporating different isotopic ratios. Unraveling this complexity requires sampling multiple comets and Kuiper Belt objects and building statistical understanding of the distribution of isotopic properties across the population. The organic chemistry preserved in Kuiper Belt objects provides clues about prebiotic chemistry, the synthesis of complex molecules before life emerged. Spectroscopic observations and analysis of cometary material show the presence of numerous organic compounds, including simple molecules like methane, formaldehyde, and methanol, and more complex species like polycyclic aromatic hydrocarbons, amino acids, and sugar-related compounds. Some of these molecules formed in the interstellar medium before the solar nebula collapsed, while others formed during solar nebula processes or on the surfaces of Kuiper Belt objects through radiation processing. Distinguishing between these sources helps us understand which organic compounds were available on early Earth and whether cometary delivery could have provided essential ingredients for life's origin. The detection of crystalline silicates in dust from some comets suggests high-temperature processing, perhaps in the inner solar nebula near the Sun, followed by transport to the outer regions, where these materials mixed with local ices and became incorporated into Kuiper Belt objects. This radial mixing, driven by turbulence and dynamical processes in the protoplanetary disk, means that Kuiper Belt objects aren't purely local products, but contain materials from across the entire solar nebula, providing snapshots of chemistry from many different environments integrated into single bodies. Modeling this mixing and trying to reconstruct the disk structure and evolution from the distribution of materials in today's Kuiper Belt objects represents an active area of research, combining observations, laboratory experiments, and sophisticated computational simulations. The size distribution and collisional history of Kuiper Belt objects also inform models of planet formation. The fact that we see both large bodies like Pluto and Eris, and also much smaller objects down to sub-kilometer sizes, tells us about the accretion process and about how efficiently small planetesimals grew into larger ones in the low-density environment of the outer solar nebula. The observed size distribution, which follows a power law for smaller objects but flattens for the largest bodies, suggests that growth proceeded relatively smoothly up to a certain size, after which further growth became more difficult, either because encounter velocities increased, making collisions more destructive than constructive, or because dynamical perturbations from Neptune's migration disrupted orbits before larger bodies could form. Cratering on Kuiper Belt objects, observed in detail on Pluto and Charon by New Horizons, and inferred statistically for other objects, provides constraints on the flux of impactors over the age of the solar system. The number and size distribution of craters tells us about the population of small bodies that existed at different times and how that population evolved through collisions and dynamical removal. Comparing crater densities on different regions of Pluto's surface revealed that some areas have been geologically active within the past 100 million years, resurfacing terrain and erasing ancient craters, while other regions preserve craters that formed billions of years ago. This geological diversity, even on a relatively small frozen world, demonstrates that we can't treat Kuiper Belt objects as simple, inert bodies, but must recognize them as complex worlds with their own histories. Future sample return missions from Kuiper Belt objects or comets would revolutionize our ability to read these messages from the solar system's dawn. While remote spectroscopy provides valuable information, laboratory analysis of returned samples allows far more precise and detailed measurements. Isotopic analysis at the level of individual mineral grains, identification of complex organic molecules that don't have distinctive spectral features, detection of noble gases that constrain formation conditions, and structural analysis of materials at microscopic scales. The technical challenges of reaching a Kuiper Belt object, collecting samples, and returning them to Earth are substantial, requiring decades of flight time and sophisticated spacecraft systems. But the scientific return would be transformative, potentially answering fundamental questions about how planetary systems form, how organic chemistry develops in space, and what materials were available on early Earth when life began. As we contemplate these frozen archives drifting in the darkness, billions of kilometers from our world, we can appreciate them not merely as distant curiosities, but as libraries of information about our cosmic origins, about the processes that created the solar system we inhabit, about the chemistry that existed before life began, about the history encoded in ice and stone that has waited 4.6 billion years for intelligence to evolve somewhere in this solar system and develop the tools and curiosity necessary to begin reading what these objects have to tell us. Every spectrum we measure, every orbit we calculate, every image we capture adds to our understanding, and the story that emerges is one of remarkable complexity, of a solar system that formed through intricate processes of collapse, accretion, migration, and evolution, leaving behind clues scattered across billions of kilometers that patient observation and careful analysis can piece together into a coherent narrative of where we came from and how we came to be. Here at the conclusion of our journey through the Kuiper Belt, as your consciousness drifts in that liminal space between waking thought and the first whispers of dream, we find ourselves at a frontier that is both physical and conceptual, a boundary where our solar system's gravitational dominion gradually gives way to the vast interstellar medium, where the familiar architecture of planets and orbits dissolves into the statistical distribution of scattered objects and eventually into the emptiness between stars. The Kuiper Belt represents more than a population of frozen worlds. It represents the edge of what we can currently observe with our telescopes, the limit of how far back in time we can directly sample materials from our solar system's formation, and perhaps most profoundly, the edge where human understanding meets cosmic mystery, where what we know fades into what we suspect, and then into what we can barely imagine. The future of Kuiper Belt exploration holds extraordinary promise. Current and planned missions may visit additional objects, building on New Horizons' pioneering reconnaissance to create a more complete picture of diversity and evolution in this distant realm. Proposed concepts include orbiters that could spend years studying a single dwarf planet, watching seasonal changes as its eccentric orbit brings it nearer to or farther from the Sun, observing atmospheric dynamics and surface processes in detail impossible during a brief flyby. Other proposals envision multi-target missions using gravity assists and extended mission timelines to visit several objects of different types, comparing classical Kuiper Belt objects with resonant populations with scattered disk members to understand how formation location and subsequent dynamical history affected final properties. Ground-based and space-based telescopes continue improving, pushing detection limits to smaller and more distant objects, expanding our census of the Kuiper Belt population and refining our understanding of its structure, composition, and dynamical evolution. The James Webb Space Telescope, with its unprecedented infrared sensitivity, will reveal details of surface composition impossible to detect with previous instruments. Future extremely large telescopes currently being constructed, with mirrors 30 or 40 meters in diameter, will image Kuiper Belt objects with resolution approaching what Hubble achieves for Pluto, revealing surface features, detecting small moons, and monitoring activity like atmospheres or possible cryovolcanism on objects we currently know only as points of light. The search for additional large objects continues, motivated partly by scientific curiosity about the outer solar system's census, but also by the tantalizing possibility of finding Planet 9 or other unexpected bodies in the most distant reaches. Every deep sky survey produces discoveries, and as survey techniques improve and telescope time becomes available, the map of the outer solar system grows more complete. We may yet find objects rivaling Pluto in size, or discover populations in regions we haven't yet thoroughly searched, or detect something entirely unexpected that forces us to reconsider our models of how the solar system formed and evolved. The Kuiper Belt also serves as a laboratory for understanding extrasolar planetary systems. As we detect planets around other stars and begin characterizing debris disks, those dusty rings of material analogous to our Kuiper Belt but around other stars, the lessons learned from our own system become crucial. We can test formation theories, constrain disk evolution models, and predict what exoplanet systems might look like in their outer regions based on what we observe locally. The Kuiper Belt is our one example where we can study a planetary debris disk in exquisite detail, where we can resolve individual objects and measure their properties directly rather than inferring population characteristics from integrated light. This makes our Kuiper Belt extraordinarily valuable for comparative planetology, for understanding whether the architecture we see as common or unusual, whether the processes that shaped our system are universal or contingent. As you drift now toward deeper sleep, let your thoughts wander among these frozen worlds, imagining the sun as it appears from Pluto or Eris, a brilliant star certainly, but one that provides only some 1,000th the light intensity we receive on Earth, barely enough to cast shadows, insufficient to provide meaningful warmth. Picture the silence, the profound quiet of an environment where there is no atmosphere to carry sound, where the distance to the nearest large object is measured in millions of kilometers, where change happens so slowly that a human lifetime would be but an instant in the slow evolution of these ancient worlds. Consider the timescales involved. Billions of years these objects have orbited, largely unchanged, carrying with them materials and information from an era when Earth didn't exist, when the solar system was a rotating cloud of gas and dust, beginning its collapse toward the configuration we recognize today. The Kuiper Belt reminds us of our cosmic context, of the fact that the solar system extends far beyond the comfortable realm of Earth's orbit, that the sun's influence reaches across billions of kilometers, organizing matter into complex structures, even in regions so cold and dark that water freezes harder than rock and methane becomes solid. It shows us that even in environments that seem impossibly harsh by human standards, geology still operates, chemistry still transforms materials, physics still sculpts landscapes into mountains and valleys and plains. The universe isn't divided into habitable and dead zones, but rather into a spectrum of environments where different processes dominate, and where beauty and complexity exist everywhere we look carefully enough to see them. The icy wanderers at the edge of sleep, those Kuiper Belt objects drifting in the twilight, where sunlight becomes indistinguishable from starlight, will continue their silent orbits long after human civilization has come and gone, after Earth itself has been transformed by the sun's eventual evolution into a red giant, after the continents have eroded and the oceans have evaporated and the atmosphere has been stripped away. These frozen worlds will endure, at least for billions of years more, carrying forward their cargo of ancient ice and organic compounds, their record of the solar nebula's composition and the processes that created planets. They exist beyond the reach of quick change, insulated by distance and cold from the transformations that affect inner solar system bodies, and in their persistence, they offer us a connection to deep time, to the realization that the cosmos operates on scales far exceeding human experience. Here on Whispering Universes, we've explored the Kuiper Belt from its theoretical prediction through its discovery, from its individual members to its collective architecture, from its formation in the solar nebula to its ongoing dynamical evolution and connection to the comets that visit Earth's skies. We've examined its physics and chemistry, its diversity and complexity, its value as a scientific target, and its role in the broader context of planetary systems. Throughout this journey, we've tried to balance technical accuracy with accessibility, to present real science while maintaining the gentle, contemplative tone suitable for sleep content. to create a picture of this distant realm that is both scientifically rigorous and emotionally resonant. As you release consciousness now and let sleep finally claim you, drift with those icy wanderers in their endless orbits. Feel yourself moving through space at speeds measured in kilometers per second, yet taking centuries to complete a single revolution around the distant sun. Experience the profound peace of existing in an environment where the pace of change is measured in geological ages rather than heartbeats, where the silence is absolute and the darkness is filled with stars more brilliant than we ever see from Earth's surface. Let the frozen worlds of the Kuiper Belt carry you gently into dreams, into that other twilight realm where consciousness and unconsciousness blend, where logic gives way to poetry, and where the boundaries we draw in waking life dissolve into something more fluid and strange. Sleep peacefully, dream deeply, and remember gently that we live in a solar system far stranger and more beautiful than our ancestors could have imagined, that the frontier extends billions of kilometers beyond the planets they knew, that even at the edge where light fades and cold dominates, worlds exist in silent splendor, waiting patiently for the day when our spacecraft and telescopes finally reveal them fully, when we truly understand the architecture of the realm, where day becomes night and our solar system finally surrenders to the galaxy beyond. Thank you for joining us on Whispering Universes tonight, for exploring these distant frozen realms together, for letting your curiosity carry you to the edge of sleep, where wonder and rest finally become one. Good night, and may your dreams be filled with starlight and the peaceful drift of ancient ice through cosmic darkness.